Hello. This is, middle of September, and we're at the end of chapter 3. I assigned problem 22 out of section 3.2, and it was this matrix, the determinant of a matrix. This is called a Vandermonde matrix. The structure you can see, it's like having a to the 0, a to the first, a to the second, b to the 0, b to the first, b to the second. So if you have a matrix of this structure, you could have a 4 by 4, and you'd have a to the third, b to the third, c to the third, d to the third, and then 1d, d squared, d to the third. And so it's a general structure called a Vandermonde, and the determinant of it is b minus a times c minus a times c minus b, which is interesting because when you look at the matrix itself, it's got 1's, a's, and a squareds, and same for b's and c's, and yet the determinant is all these first power things. So let's see, how would you do a problem like this? Well, just do what it says to do. Do the determinant on this side. I'm going to do the cofactor minors along this 1, just so I multiply by a 1 in front, and there's the Cocoa Bananas. She says hello, hello, hello. All right, anyway, so that's where these 1's come from, and that's a negative 1 there because that's this 1, but it's in an odd position because it's second row, first column. 1 plus 2 is 3. So we have a negative 1 on that guy. And you do the little 2 by 2s. Oh, you want to get down? Okay. Okay. She wants to get down. So say bye to the Cocoa Bananas. She's gonna go down and do her thing. There you go, Louise. Anyway, so when you have this 1, the cofactor minor is this 2 by 2, b times c squared minus c times b squared. So it's bc squared minus b squared c. That's right there. These other 2 come from those other 2 cofactor minors. Now on this side, you really have no choice other than to multiply it out. So I did this binomial times this binomial. There's no like terms, so it just stays expanded like that. Then I multiplied through by c, I multiplied through by negative b. And imagine you doing this, say on a test or something, and as you're multiplying out, you hit this negative ABC. And you say, oh my God, there's nothing like that over on this side. There's no ABC. So what are you going to do? You got to do the thing out. You still got to multiply through by the negative b. And as you multiply through by the negative b, check it out right there. Plus ABC happens. From the negative b times the negative AC, you get a positive ABC. These 2 weird ducks cancel. And that's why, if you try doing this as a straight out homework problem, because I assigned it to you, you might not get this side, or sorry, this side here with just the AB squareds and a squared b's and stuff. You might not get this side to factor like this, because to make it factor like that, you would have had to plus and minus an ABC to make it happen. Oh my God, you would have never thought of it. It would never come to mind, So that's problem 22, and here's one of the reasons why I assigned the problem. This is a chapter of my dissertation that was published as a paper years ago, and the big theorem, our big theorem, its proof uses. Let's see if I can get that to appear. I'm going to point to the Vandermonde matrix that we got right here. So P sub 1 is a number, and I have powers, because it's 2 to the P sub 1, 2 to the P sub 2, 2 to the P sub 3, and then there's 1's here. So this is like a version of a Vandermonde matrix. Here we have the 1's in a column. This one we have the 1's in a row, but it's still a Vandermonde matrix. It's very cool. And the big deal about it is this. As long as the A and the B are not the same number, the A and the C are not the same number, the B and the C are not the same number, the determinant is non-zero. And we needed to have a non-zero determinant for this calculation. And my advisor was so jazzed when he saw, it's a Vandermonde matrix. And I just said, what is that? I don't know what that is. He says, it means we win. It means we've got the theorem. He's very excited. Anyway, let's go to the next assigned problem. It's resumed. Ha! All right, so it's problem 16 from 3.3 they asked you to take a look at. And they give you the vertices of a parallelogram, and they'd like to get its area. Now, we didn't do this formula in class, but it's in the book. So you If you look in that section, example 3, you can get the area of a triangle from just its vertices using this formula. It's 1/2 the absolute value of the determinant of this matrix. And there's your ordered pairs. See, x1, y1, x2, y2, x3, y3. So here's what we're going to do. I'm going to throw in this diagonal. And I'm going to find the area of that little triangle right there. So, erasing and substituting in. It doesn't matter the order because of the absolute value. I'll talk about that in a second more. I'll do the 2, 3. I'll do the 5, 3. And I'll do the 4, 5. Okay. So now we got to do that determinant. Now, if you switch 2 rows, you get the opposite sign. That's a property of determinants. So that's why the absolute values. Because it doesn't matter which order you do the points, the calculation is going to come out to be the same. The absolute value takes care of whether the calculation comes out positive or negative. Doesn't matter because you're taking the absolute value. And there's this half in front. So let's do this. Let's go right along this column here. So I'm going to have 1/2 times. Now this position is first row, third column. That's worth a 4. So it's a positive position. So I have to do 25 minus 12 is 13. Now I got to do this guy. That's going to be a minus. And I'm going to have this little 2, 3, 4, 5 guy. So it's 10 minus 12. So it's minus -2. So it's a +2. And then this last spot, that's a positive spot. And I'm going to have 10 minus 12. That's a -2. So I've got, let's see, I've got the 13/2 for this piece here. And I'm going to do the other triangle now. Let me just write down 13/2. That doesn't feel right. We did this one in class. We didn't get 13/2. Let me just double check. For this one, it's 25 minus 12. 25 minus 12 is 13. For this guy, it's 10 minus 12 is -2, but it's -2. And for this guy, it is 6. Oh, yeah, I did the same thing twice. Okay. It's 6. 6 minus 15. 6 minus 15 is 6 minus 15. I think that's -9. Okay, that's better. So now I'm getting 15 minus 9. That's 6 over 2 is 3. And that's correct. The area of this triangle is 3. It's not going to be a very big area. I mean, look at those coordinates. Glad I caught my mistake. So the other one, the other calculation is actually pretty easy to do because you're going to keep the 5, 3 and the 4, 5 because that side is shared by both triangles. You're just going to put a 7 and a 5 in here. And let's do that one. So we got to remember that 3 from before. I'll write it right here. Okay, so this one's going to be 1/2. And remember it's absolute value. Let me put absolute value down in case I get a negative inside. All right, so this one is times 25 minus 12. Oh, I did that. 25 minus 12 is 13. This one is 35 minus 20, and it's an odd spot, so it's minus 15. 35 minus 20 would be 15, but it's an odd location, so it's an extra minus sign times it. And now this guy is going to be 21 minus 25. That's -4. But it's absolute value. So I'm getting -2 minus 4 more. That's the absolute value of -6 over 2. And that's 3. So that triangle is also area 3, which is a property of parallelograms. A diagonal of a parallelogram cuts the parallelogram into 2 congruent triangles. So getting those 2 areas the same, that's really good news. And in fact, the area is 6. You can do it as a geometry problem by simply noticing that if you came straight down here, it's the same as this triangle over here. And this is just a little right triangle. You can calculate its area. Actually, this thing's a rectangle now. And that rectangle is the same as the area of that parallelogram. And it turns out to be 6. So that was the 2 problems I asked you to look at. Now, we did in class some ideas. I'm going to put those in the next video.